Now, sometimes you would, see people referring to zeros and poles at infinity. Okay. So sometimes we specify that, but sometimes we don't. But what does that mean if you see something like that? So when you say that something has a 0 at infinity, it's basically saying that the Laplace transform goes to 0 for s going to infinity. And when can that happen? So it actually happens in this case, right? If s goes to infinity, then because there's a square, you have a higher order in the denominator than the numerator. Therefore, this goes to 0 as s goes to infinity, right? So for this case, whenever you have a higher degree in the denominator, you can say that there is a 0 at infinity. Vice versa, if you have a higher degree in the numerator, it goes to infinity when s is infinity. So when you have a higher degree in the numerator, you can say that there is a pole at infinity. Okay? So this is just something to know, okay, if you see it. All right? So maybe a remark. Okay. You can have 0 at infinity or minus infinity if x of s goes to 0 as s goes to plus or minus infinity, right? And a pole at this if x of s goes to infinity as s goes to plus or minus infinity. So let's do one more example. So here we have x of t equal to a delta function plus two terms here, which are actually both right-sided exponentials as well, right? One decreasing, one increasing. Okay. So we know how to deal with the last two, the second and third terms, but we haven't dealt with this first term yet. But the first term is rather straightforward. So suppose you want to find the Laplace transform of this delta of t. All right, by definition, this is the integral of delta of t times e to the minus st dt. Okay? So delta of t is non-zero only when t is equal to 0. But when t is equal to 0, this exponential is 1. Sorry. So when the exponent is 0, this is 1. So this is equivalent to taking the integral of delta of t times 1 dt. And the integral of this is just 1, right? And this integral holds no matter what value of s you choose. So the region of convergence is any value of s, right? Includes any value of s. So the region of convergence is the entire complex plane, or the entire S plane. Okay? All right. So then, we can get the Laplace transform of x of t, right, which is 1, right, which is 1 when you take the Laplace transform of delta of t minus 4 over 3, 1 over s plus 1, plus 1 over 3, 1 over s minus 2. Okay? So the region of convergence of 1, right, is any value falls within the region of convergence. So we just need to look at these two terms here. So for this term, the region of convergence is the real value of s greater than minus 1. And for this is the real value of s greater than 2. Okay? So if you take the intersection of both of these, your overall region of convergence should be the real part of s greater than 2. Okay? So if you further combine all these three terms, you get s minus 1 squared over s plus 1, s minus 2. And for real part of s greater than 2. Okay. So let's visualize this, try to visualize this on a complex plane. So this is the real part, this is the imaginary part. Okay, suppose 1, 2, 1, 2. Okay. So first of all, the region of convergence is all values of s who has a real part greater than 2. So the region of convergence is this half plane to the right of 2. Okay? So this is the region of convergence. Right? Now, if you look at the numerator, you have 2 zeros at 1. Okay? So let's draw 2 circles here to indicate that we have 2 zeros at 1. And we have a pole at minus 1 and a pole at 2. So let's draw a cross at 2 and a cross at minus 1. Okay? Right. So this is how you, visualize the Laplace transform on the complex plane. Okay? Now, just to take note here, since we have the same degree in both numerator and denominator, therefore, there are no poles or zeros at infinity. Okay? All right. Now, if you think about it, the Fourier transform is a special case of the Laplace transform with s equal to j omega. Okay? So when you're looking at a Fourier transform, you're actually looking at a Laplace transform for values of s that lie on this line here. Okay? That lie on the imaginary axis. Okay? But since the imaginary axis here does not fall within the region of convergence, therefore the Fourier transform does not converge in this case. Right? So the Fourier transform does not exist in this case because the ROC does not include this j omega axis. Okay. Okay. So any questions up to this point? So when I try to understand this Laplace transform, I think this thing that we mentioned at the very beginning was very critical for myself, right? So, viewing the Laplace transform as a Fourier transform of this sort of, modulated signal x of t, right, is a very important concept, right? So right, the Laplace transform is the Fourier transform of x of t times e to the minus sigma t. And the region of convergence is basically specifying when this x of t times e to the minus sigma t is absolutely integrable, right? When this x of t times e to the minus sigma t has a Fourier transform, okay? So if x of t is this, increasing function to the right, then your sigma should be large enough in order to suppress it, okay? So when you need sigma to be large enough, this corresponds to a region of convergence. This corresponds to a region of convergence that is on the right-hand side, okay? So you need sigma, right, the real part of S to be large enough, okay? Now, on the other hand, if you have a signal, if you have a red signal that increases on the left-hand side, then this exponential should instead suppress the left-hand side, meaning that sigma should be negative, right? So in that case, sigma should be small enough, okay? And a small enough sigma corresponds to a region of convergence that is on the left-hand side, right? So if you recall in 9.2, we are indeed looking at a signal that is left-handed, okay? All right. Okay. So we can sort of observe a few things here, okay? So first of all, you can observe that the region of convergence of x of s consists of strips parallel to the j omega axis in the s-plane, okay? So you can see that all of these regions of convergence, they are always parallel to the j omega axis. And this is because, the value of the imaginary part does not really affect the convergence. What really affects the convergence is the value on the real part, right? This sigma value, okay? So what really affects the convergence is this sigma, right? The imaginary part, does not affect the convergence. The imaginary part is just something that oscillates, okay? All right, so, this first property tells you that the region of convergence must be something that is parallel to the j omega axis, okay? And this is because our key is to determine if this x of t times e to the minus sigma t converges. And whether or not this converges depends only on the real part, which is this sigma, okay? Now, secondly, we can see that for rational Laplace transforms, the ROC does not contain any pole. And this is obvious because for a pole, if you substitute a pole inside x of s would be infinity, meaning that it's not converging, okay? So the region of convergence cannot contain any pole, okay? So this is because, x of s is infinite at a pole, okay? Now, property 3 says that x of t is finite. If x of t is finite duration, right? If your x of t is just some finite duration, then it's already, right? It must be absolutely integrable, right? No matter what the value of sigma is, okay? Because if x of t is finite duration, then your Laplace transform is always integrating over a finite duration. So when you integrate a finite function over a finite duration, it can only be finite, right? So if x of t has only a finite duration, then the ROC is the entire S-plane, right? Any value of S would hold, right? Would have a Laplace transform, okay? Now you can actually, prove this, right? It's actually